Hey guys, Mrs. O'Donnell here. Today we are going to be working with properties of radicals and operations with radicals. Our goal is to develop some procedural fluency and number sense working with basic radical expressions. We do have a jam-packed week. Make sure you are reaching out to me if you have questions. Hop on to my virtual office hours. 7:30 to 8:30 a.m. Monday through Friday, or 1 to 2 p.m. Monday through Thursday. If you come to that early morning session, you'll get to have breakfast with me and my kids. So a little extra incentive for you there. All right, so go ahead and pause the video here, try this warm-up, and then come on back and we'll check answers. All right, so it says, what are the solutions to the following quadratic expressions? So we know this first quadratic is being shown as a system. So the solutions are actually the intersection of the system. So our solutions here are going to be at -3, 2, and at 1, 2. That would be our solution set to that system. Okay, over here next we've got this factored form, -3 x minus 5 x plus 11. So we can use that zero product property. And I know the number that plugs into x here that will make this factor 0 is 5. And the number that's going to plug in here that's going to make the second factor here 0 is going to be -11. Notice I don't really have to do much with this first factor because there's not a variable there. -3 is just never going to equal 0. There's no way to make that happen, right? So my solutions here would be x equals 5 and -11. Okay, and then this last one here, x squared minus 3x equals 10. I know I have to get it into some other kind of form to see what it looks like. You could graph this, right? We know that you could graph this as a system, x squared minus 3x, and then also graph the constant 10 and just see where they intersect. We could put it into standard form by subtracting 10. So we've got x squared minus 3x minus 10 equals 0, and then we could find our vertex, make a t-table, and do some graphing there. Or we could check and see if it factors. I think this might factor pretty nicely here. So let's see here. If I do my area model, I've got x squared, I've got a -10, and I know my diagonal is going to add to make -3x. And let's see here, x times x makes x squared. My options for 10 are really 1 and 10, 2 and 5, but I know I'm trying to make a 3, so 2 and 5 seem pretty good. I know I want the 3 to be negative, so I'm going to make that 5 negative because it's the bigger of the two numbers. So I would end up with -5x and 2x, and 2x plus -5x, yep, that makes that -3x. So this shows me that my factors are x plus 2 times x minus 5 equals 0. And now I can use that zero product property. I can see that right here I would plug in a -2 to make this first factor go to 0. And for my second factor, I could plug in a 5 to make that factor go to 0. So my solutions are -2 and 5. All right, so let's talk about radicals and roots. So we learned our laws of exponents. We have this fractional exponent rule where if we have our base raised to a fractional exponent, then we know what the number in the numerator is that exponent, and the number in the denominator is that index in our root. So for example, if I had x to the 5/7 power, I could rewrite that or convert it to be equal to the 7th root of x to the 5th power. So just like working with exponents is related to multiplication, finding roots is related to division. The square root is the inverse operation to the square. All exponents have an inverse root operation. The tricky part about roots is that we often need to simplify them to find an exact answer instead of rounding, which isn't as precise. All right, so we often need to simplify our radicals, right? So there's two main strategies to help you work through simplifying radicals. Factor pairs, you're really just looking for perfect squares, right? Or perfect whatever root it is you're working with. We're going to primarily work with square roots in this unit. So if we're looking for factor pairs, you need to really know what those perfect squares are. And one thing that can help you with that is kind of going off to the side and just making a quick, like jotting them, charting them out, right? So 1 squared is 1. That one doesn't help us too much, right? 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared, 6 times 6 is 36. 7 squared, 7 times 7 is 49. 8 squared, 8 times 8 gives me 64. 9 squared, 9 times 9 is 81. 10 squared, 10 times 10 is 100. We could keep going. 11 squared, 11 times 11 is 121. And then 12 squared, which I think I'm running out of room to write, is 144. All right, so if I want to go ahead and factor 60, I want to look for what kind of perfect squares do I see that 60 is going to divide by. And if I'm not sure, I could just grab my calculator and try some things, right? 60 divided by 25, nope, that didn't work. 60 divided by 9, does that work? Nope, that doesn't work. 60 divided by 16, nope. 60 divided by 4. All right, now I got something. So I did 60 divided by 4, and that gave me 15. So I've got the square root of 4 times 15. Okay, and there's a special thing happening with simplifying radicals that when you multiply, okay, radicals, you can just multiply them together under the radical, or you can also split them apart. So I can do the square root of 4 times the square root of 15. So if I take the square root of 4, I end up with 2. And I don't have anything left. 15 doesn't break down any further, so I would end up with the 2 times the square root of 15 would be the simplified form of 60. I could also do this by prime factorization, right? So if I'm not sure what, perfect square 60 divides by, I could grab 60 and I could just start dividing. 60 divided by 2, 30 divided by 2 is 15, and hey, 15 divides into 3 and 5, so my prime factorization would be 2 squared times 3 times 5, and since I've got a square right here, I know that, this is all under my radical or my square root, so I know that I actually can do the square root of 2 squared and get 2, and I'm left with 3 times 5, or 15, underneath my radical symbol. You can add and subtract radicals as long as the root and what is under it match or create like terms. So, for example, you're kind of treating it like a label. 2 square root of 2 plus 3 square root of 2, well, that gives me 5 square roots of 2. Or 12 square root of 7 minus 3 square root of 7, well, 12 minus 3, that gives me 9 square root of 7 plus 5 square root of 2. Well, I can't, square root of 7 and square root of 2, those are two different labels, right? I can't add those. So I would just have to leave it as 9 square root of 7 plus 5 square root of 2. Okay, go ahead, pause the video, take a couple minutes to try some yourself. You may have to do some simplifying as you go. You can also easily multiply radicals by just multiplying what's underneath the radical symbol. So for example, the square root of 2 times the square root of 6, that gives you the square root of 12. Now when you do this, you might end up with a radical that can now simplify, right? Square root of 12 has a perfect square inside of it. 12 divides by 4. So let's see here, if I come sort of off to the side here, my square root of 12 splits down into 4 times 3, right? So my square root of 4 times my square root of 3 gives me 2 square root of 3, right? So this can even be simplified further down to 2 square root of 3, okay? You can also multiply problems like 3 square root of 3 times 5 square root of 6 by, again, you can multiply your whole numbers. 3 times 5 is 15, and you can multiply your square root of 3 times your square root of 6, which gives you your square root of 18. And now at this point, that square root of 18 can simplify even further, right? So 18 breaks down into square root of 9 times the square root of 2. Square root of 9 is 3. So 15 times 3, that gives you 45 times the square root of 2. Okay, and all I used here is that commutative property of multiplication. Okay, same thing goes for dividing. All right, if you're able to, you can divide a square root by another square root. It is bad form to have a square root in the denominator, so we have to do what's called rationalizing the denominator. Okay. Here, in this case, I could do my square root of 5 times over my square root of 5. So I end up with 2 times the square root of 5, which is my square root of 10, over square root of 5 times the square root of 5. Well, that's the square root of 5 squared, which gives me just 5. And I can't simplify that down any further. Okay, over here on the right, we could try simplifying it down a little bit. 6 divides nicely by 2, and that leaves us with 3 square root of 2 over the square root of 10. I need to get rid of that square root in my denominator, so I'm going to rationalize it by multiplying the square root of 10 over the square root of 10. The reason we're allowed to do that is because we're really just multiplying by 1. Okay, when we multiply by the square root of 10 over the square root of 10, we haven't changed our problem at all because we're just multiplying by 1. It just looks a little different, right? But anything over top of itself is equal to 1. And when I do that, I can multiply what's underneath my radical symbol. So 2 times 10, that gives me 3 times the square root of 20. And square root of 10 times the square root of 10, well, that's the square root of 10 squared, which is just 10. I don't think, 20 does simplify. 20 has a 4 in it, right? So let's see here. That's going to simplify down even further. 3 times the square root of 4 times the square root of 5 over 10. Square root of 4 is 2. 3 times 2 is 6. Square root of 5 over 10. And it looks like that 6 and 10 will even simplify down. Those both divide by 2, so that gives me 3 square root of 5 over 5. Kind of ran out of space there. And that's really the nut and bolts of what we've got going on today. Hopefully that was a quick review for you. Hop on, do today's Google form, and make sure that you work on your Delta Math assignment. Thanks so much. I hope to see you in office hours with any questions you may have.